So as I told you, after 1935 Bihar Nepal earthquake and after the Quetta earthquake, GSI published a map based on the isoseismal lines, or you may say the modified Mercalli intensity scales value of the earthquake happened in the previous 200 years. And then using those values, they prepared a seismic zonation map of India. And that map was basically published in 1962. Thereafter it went on to the revision in 1966, and these two maps that you see here are basically the seismic zonation map prepared in 1962 and 1966. And thereafter what happened, you know, like Deccan Plateau was kept in the safe zone, or so-called safe zone, and earthquake happened. That is the Koina earthquake, 1967 Koina earthquake, very infamous one, caused a lot of casualties, and because of this particular earthquake there was a need to revise the zonation map further. Okay, so they have also taken into account the updated geological, geophysical and the seismological information, and thereafter the zoning map of 1966 went through major revisions, and in 1970 a new map was published, and in this new or revised map the number of zones were reduced from 7 to 5, 1 to 5. Okay, and the major change was they have completely removed the zone 0, and because it was basically inappropriate to keep a 0 zone for a particular region where the earthquake has already happened. So they wanted to remove the 0 zone, so the zone was removed, and then they came up with the seismic zones amounting to only 5, 1 to 5. Okay, and based on the probable maximum intensity scale, or MMI scale, 5 to 9 and more. Okay, now this is the map of 1970 in the left hand side. So you can see they removed the 0 zone completely. Instead they put the Deccan Plateau and the surrounding region in zone 1, and still the northeastern India and the northern region were kept in the zone 5. And then there were some smaller modification happened in 1984, and thereafter in 1993 Latur earthquake happened of magnitude 6.3, which was having an intensity of around 9 on the MSK scale, and Latur being classified in the seismic zone 1 at that time, an area not expected to experience such strong earthquakes. Okay, and there in that particular part of the Deccan Plateau, Jabalpur 1997 earthquake happened. Thereafter in the Gujarat region, the 2001 Bhuj earthquake happened, and basically all these earthquakes basically raised the concern about the accuracy of the seismic zonation map of the peninsular India. So map went through the revision in 2002. The new map was published that was having the seismic zone starting from 2 to 5, and zone 1 and 2 were merged together. Okay, so Latur region reclassified has been reclassified into zone 3 into the new zonation map, and zone 5 represent the highest seismic risk and includes regions that have experienced some of the India's most devastating earthquakes. Okay, so seismic zone 5 includes the region of Andaman and Nicobar, northeastern India, northwestern Bihar, Kangra Valley, eastern part of Uttaranchal, run of Kutch, and two densely populated cities were also marked as the high risk regions, such as Delhi in zone 4, Kolkata is also located at the boundary of zone 3 and zone 4. What is the seismic zone of Dhanbad? Zone 3, right? What is the seismic zonation of Delhi?
4.
Seismic zone 4, right? So the 4 seismic zones are assigned peak ground acceleration values ranging from 0.1 G to 0.4 G. Okay, now look at the table here. So these are the PGA, expected PGA values in these regions. Second being 0.1 G, third being 0.2 G, likewise seismic zone 5 being 0.40 G. So this is the final seismic zonation map that we still consider today. So that is having the zones starting from 2nd to 5. Okay, so have you seen this map before? There were some individual previous studies happened in terms of the zonation. So the zonation studies that we were talking about were conducted by Bureau of Indian Standard or JSI or some other agencies. But there were some individual workers, those who also did some zonation studies, especially Tandon in 1956. He came up with the seismic zonation map of India, and it consisted of only the 3 zones, majorly based upon the time-space relationship of the earthquakes. And then in 1962, Guha classified the entire India into 5 seismic zones based on the intensities of 35 major earthquakes happened in between 1827 to 1950. Thereafter, Gubin in 1968 considered the data of various themes of the seismic zonation of Indian peninsula, like he also considered the geology, tectonics of the region, and then he also considered the seismicity of the past earthquakes. And then he classified the entire India into 16 seismogenic zones. Okay, and thereafter probabilistic seismic hazard analysis was conducted by Basu and Nigam in 1978 for the zoning purposes, and then he came up with the seismic hazard map in terms of the peak ground acceleration for a period of 100 years with the probability of exceedance of 0.63, and the earthquake data of 55 years from 1917 to 1972 was considered for the analysis. And thereafter Khatri came in 1984. He considered 24 seismogenic sources. He divided entire India into seismic sources zone in terms of the polygons, and then he made a seismic zoning map in terms of the peak acceleration for 50 years for a probability of exceedance of 10%. And then Parvez in 2023 came, and he also prepared a first order seismic zonation map of India and its adjoining region using the approach of deterministic seismic hazard analysis using realistic. He was the one, he used the realistic strong ground motion data for its model for the seismic hazard zoning map. And then he also took into consideration of all the available geophysical data, geological information, and also he performed the extensive research and divided the entire subcontinent into 15 regional polygons based on their structural model, seismic zones, and the attenuation structure and other input parameters he also considered, such as the focal mechanism and the earthquake catalog. So this is Khatri, who divided the entire India into 24 seismogenic zones. Okay, he made up several polygons in terms of the seismogenic sources. Thereafter, he tried to calculate the seismic zoning map of India. So he made the seismic zoning map of India in terms of the contour of the peak acceleration, and then he calculated the probability of exceedance equal to 10% during a period of 50 years. Okay, then Parvez et al. 2023, he basically designed the hazard parameter in terms of the design ground acceleration, peak ground velocity, and peak ground displacement. Okay, and he observed, or his map observed basically northeastern part of India under great stress, and between the Eurasian plate in the north and the Myanmar plate in the east, and the DGA means design ground acceleration, which was varying from 0.15 G, 1 G to 1.3 G, with the maximum observed around the zone of 1897 and 1950 earthquakes. So these are the maps that he produced for the peak ground acceleration, and this is for peak ground velocity, and this is the map for peak ground displacement. the most famous one that you will hear very frequently is the Global Seismic Hazard Assessment Program. Okay, so in short, it is also known as GSHAP. Okay, which was basically given by Bhatia in 1999, and he used a probabilistic seismic hazard analysis approach to do the zonation of India. Okay, and it was done under the banner of Global Seismic Hazard Assessment Program. So he basically divided entire India into 86 potential seismic zones, okay, for the probabilistic seismic hazard analysis. And then, so this is the seismic source zone map of India, which was considered by Bhatia. He did not even do it for India, but also for the adjacent region of India. So entire Indian subcontinent was basically considered in this seismic zonation map. So they identified, as I told you, 86 seismic source zone, and hazard level was considered in terms of the peak ground accelerations, and they used the global relationship for finding the PGA values. The attenuation relation they used was global, was basically given by Joyner and Boer in 1981. This was also the drawback of this particular zoning done by Bhatia et al, because they used the global relation, attenuation relation. Although they could have used, they should have developed the site or locally developed attenuation relation for doing the zonation of Indian subcontinent. So the PGA was computed for a probability of exceedance of 10% in 50 years. Okay, so what is the probability? The 10% probability in 50 years. The PGA was developed. The PGA varies from 0.05 G to 0.5 G. The hazard level is higher along the plate margin, so that is natural along the plate margin because a lot of earthquakes are happening, so it will be naturally high. So the PGA or hazard level was considered to be very high. So this is the PGA map that was given by Bhatia et al in 1999. Okay, now so the expected PGA for Yuma Arakan ranges was the highest, with the values ranging from 0.35 G to 0.4 G, and for the peninsular India 0.05 G to 0.1 G. The hazard map was broadly classified into 4 zones with the hazard parameter as 0.1 G, 0.2 G, 0.3 G and 0.4 G. So you can see in the table seismic zones 1, 2, 3, 4 were classified, and then the PGA was assigned to each of the seismic zone. Okay, the ranges are given in terms of the PGAs. Okay, so basically there were some drawbacks for this zoning map. So the drawbacks were they used the Joyner and Boer attenuation relationship for entire Indian subcontinent. Okay, and which is basically applicable to a particular region that was developed for a particular region somewhere else. Okay, but they used it for entire Indian subcontinent. They should have developed their own relationship and then could have incorporated into their study. That was one of the drawback, because Indian subcontinent has a very diverse set of geological and the tectonic setting. Okay, for that purpose a new and or maybe related to a particular area or geology, the attenuation relationships should have been developed. PGA estimated by Bhatia et al were basically underestimation. So when they compare the PGAs given by Bhatia with the real earthquake scenarios, then they found that the PGAs whatever was calculated by Bhatia were basically lower than the actually happening in case of the real earthquakes. Okay, and the PGAs of some, so if you compare the PGAs given by Bhatia and the previous earthquakes happened. So in 1995 the Kobe earthquake happened in Japan. Okay, as per the GSHAP Bhatia, as per the Bhatia et al, the PGA should have been in the range of 0.4 to 0.48 G. but 0.7 to 0.8 G PGs were observed. So that is the underestimation. 2001, when the Bhuj earthquake happened, expected PGA values were 0.16 to 0.24 G, but actually 0.5 to 0.6 Gs were happened. Okay, that is also underestimation. In 2003, when the Algeria earthquake happened, 0.08 to 0.16 G were expected, but actually 0.3 to 0.4 G PGs were observed. Okay, likewise 2003 Bam earthquake in Iran, 0.16 to 0.24 G were expected, but much more higher PGA values were actually recorded. Okay, so it can be seen that the ground motion given at a regional scale is insufficient for the hazard assessment, and the hazard estimation has to be addressed at a local scale. But nevertheless, the seismic zonation map can still provide a guideline for the building codes and the future planning. So this is basically all for that I wanted to convey about the seismic zonation happened in India. So we have covered so far. Initially, we were covering what is zonation, what is seismic hazard and risk. Thereafter, we graded the seismic zonation into nano zonation, macro zonation, macro zonation, and they further classified the micro zonation into several grades: grade 1, grade 2, and grade 3. Okay, and thereafter we talked about these grades in detail based upon their scale of the study, and after that we also discussed about the seismic zonation happened in India so far. So like 1935 GSI developed seismic zonation map based on the isoseismal lines. Thereafter it went on to the revision in 1966, and then after the Koina earthquake another revision happened in 1970, and then 1984 another revision happened. Thereafter 1993 the Latur earthquake happened, and that also necessitated the need of revising of the seismic zonation map. Okay, so finally in 2002 the final map was published, which is still used for the seismic zonation map of India. Now, as I told you, we can also, I wanted to discuss about the surface waves. Okay, so you know the surface waves are long period high amplitude waves if you compare it with the body waves such as P and S waves, right? And when you see surface waves coming from the larger distance, the seismogram is mostly dominated by the surface waves, okay, because the P and S waves get attenuated as they travel larger distances. So if you compare the attenuation or the geometrical spreading factor for the surface wave to that of the body waves, so the surface wave energy decays with respect to distance as 1 by r, okay, but the body waves, if you compare it with the body waves, it basically decays as 1 by r square, because the body waves are traveling in the spherical wavefront mode. Okay, so per unit area 1 by 4 pi r square, so 1 by r square. But if you look at the surface wave, they are mostly traveling on the surface in the circular format. Okay, so the perimeter of the of the circle is 2 pi r, 1 by 2 pi r. Okay, so that is why the decay of the body waves happens faster in comparison to the surface wave. Now, if you look at the damage, the surface wave, because it is large amplitude waves, they can cause damage to large buildings at a relatively far distances, more than 50 kilometers, and body waves near an epicenter typically are higher than 1 Hz, which is near the resonance frequency of the small building like houses. So body waves basically has their frequency near about 1 Hz. So this is similar to the small buildings and houses. So the resonance may occur, and because of which the damage may happen due to the body waves. And surface waves have lower frequencies which are near to the resonance frequencies of the larger building. So surface waves generally cause damage to the larger buildings because their frequency comes into the resonance of the larger buildings. Okay, that is why they occur a lot of damage due to the resonance phenomena that happens. Now, if you surface waves are basically sensitive to different depths within the earth depending upon their frequency. For seismologists, this makes them very handy for determining upper mantle structure. We look at surface wave properties as a function of frequency and then use this to interpret earth structure at various depths. So they are basically talking about the dispersion phenomena. Okay, dispersion is basically, if you talk about the dispersion of light, what happens when a white light falls upon the prism? Because of the difference in the reflective index and the apex angle, the dispersion happens. The white light will be divided into its several distinct colors, okay, based upon their frequencies. Similarly, in case of the surface wave, what happens? The different frequencies of the surface waves travels at different speed. Okay, so when you will plot those frequencies, velocities with respect to its wavelength or frequency or maybe with respect to the period, then whatever curve you will find, that is known as the dispersion curve. Okay, so we will look at that in detail. Now look at this particular diagram. Actually it was an animation, due to the PDF it is not working. So surface waves are basically of two types. One is Rayleigh wave, another is love wave. Okay, so Rayleigh waves basically travels. So what is the particle motion of Rayleigh wave? Retrograde elliptical. Okay, so if the particle, if you look at the particle near to the surface, okay, so particle is basically moving like this. Okay, if the wave is moving like this in this direction, the particle will move like this in the elliptical format. Okay, but retrograde elliptical. Retrograde means near to the surface, the Rayleigh wave is passing like this. Near to the surface, the particle motion is in opposite direction. Okay, that is the retrograde. Okay, so retrograde elliptical motion it has. So and if you look at the love wave, in the case of love wave, the particle motion is horizontal. Particle motion is horizontal but perpendicular to the motion of the wave, right? So love waves are mostly consist of SH wave energy. Okay, horizontal component of the shear wave energy, but the Rayleigh waves consist of the P wave energy and also the SV wave energy. Now if you look at this particular seismogram here, what do you see in this seismogram? This is the three component seismogram of a earthquake. To be very exact, the earthquake happened at a shallow depth in the Vanuatu island, that is nearby the New Zealand. Okay, and what do you see in this particular seismogram? There are three components. In the top you have the radial component, in the middle you have the transverse component, thereafter you have the vertical component. Okay, so in all these three seismogram, if you look at the top one and the bottommost one, they are having very high energy of surface waves. Okay, in the transverse also you have the energy, but that is only mostly related to the love wave. Okay, because love wave consists of SH wave motion, and SH wave are vastly recorded onto the transverse component. But radial component or the vertical component, if you will look at, the Rayleigh wave is there. And if you look at the love wave and the Rayleigh wave, which is coming earlier? Love wave. So generally love waves are faster. Okay, it is also said that the love waves or the Rayleigh waves love waves are basically around 1.1 times faster than the Rayleigh wave. Okay, now look at this one. Certain studying the previous and previous study is a radial and vertical in that the surface wave section of theta. Why is it that the coordinate means like between decreasing that increasing here? As I told you, like if you look at, so because this earthquake is recorded from a very large distance, that is why surface waves are very clear. onto this seismogram. Okay, so it is coming from a larger distance, and while covering that larger distance, as I told you in my previous slide, the attenuation factor for the body waves is proportional to 1 by r square, but for surface wave 1 by r. So body waves are getting attenuated faster than the surface wave. So that is why you can say, or generally speaking, the body waves are of smaller amplitude than the surface waves. Okay, so that is why you see the surface waves are of higher amplitude, large period wave train here, right? So now, if you move further, the surface waves in this particular figure. Okay, so this figure you can see you have 3 direction x, y, z. Okay, there is transverse direction, there is vertical direction, and if you join the source to the receiver, that is your radial direction. Okay, so love waves, as I told you, results from the SH wave that are trapped near to the surface, and Rayleigh waves are a combination of P and SV wave. Okay, so the motion that you see in XZ plane is associated with the Rayleigh wave, and perpendicular to this plane there is the motion there, but perpendicular to the travel direction of the Rayleigh wave, or sorry, love wave, that is your SH wave motion. That is for the love wave motion. Now, okay, so as I told you, the surface wave attenuation factor is very small, little smaller than the body waves. So surface waves do not basically attenuate faster in comparison to the body wave. So as the surface wave travels, because of its geometrical factor, it basically circles the earth multiple times. Okay, so you will see multiple surface waves onto your seismogram. Okay, multiple times they can travel because they are not attenuating faster. Okay, but it is attenuating. Attenuation is also an important phenomena. Okay, if the attenuation is not there, then these waves will keep on continue to travel all across the globe. Okay, and then finally what will happen? It will shatter the entire earth, because the waves are basically revolving all around the globe continuously, no attenuation is happening. Then what will happen? Finally the superimposition will happen, and more waves will be generated, and finally the entire earth will be shattered. Okay, so attenuation is a very important phenomena. So attenuation must happen in order to reduce the amplitude, and finally they will decay out. Okay, so basically in this particular diagram, what you see, this is the travel time curve of the Rayleigh and the love wave.
Is it visible?
So what you see, there is, let's suppose there is this earthquake. This is the globe. Okay, on you see there is an earthquake, and we have a station here, right? From the earthquakes, the rays are traveling in anti-clockwise direction, if you will see. Okay, and we are talking about the Rayleigh wave first. Okay, similarly you can extend this particular thing for the love wave as well. Okay, so when they are traveling in the clockwise direction, then the rays are traveling from earthquake to the station, and we call it R1. When they take one complete round and travel back again to the station, then you have R3. But in between, the rays have traveled in anti-clockwise direction and reached to the station. That we call it R2. Okay. Likewise, R4, then R5, R6. Okay. So this is the travel time curve. Travel time curve, you know what is travel time curve? Okay, travel time curve is, let's suppose you have this is the globe of the earth. Okay, there you have an earthquake. Okay, you have some stations here, 1, 2, 3, or maybe 4. Okay, the earthquake energy has reached here, let's suppose P wave energy. Okay, and the seismic station here has recorded a seismogram, the P waves like this, maybe. Okay, then because the second station is little farther away, then the P wave energy will be basically recorded little later. Okay, so you can see the starting point of the P wave is little later. This is your time, okay, this is your time, this axis is time. Okay, so upward the time is increasing. At the third station, because it is much farther, so the P wave energy will reach there little later. Likewise, it will keep on happening. Okay, so this is your time, and here you have distance from the earthquake to the station location. Okay, so when you will join all the arrival points of the P wave, arrival time of the P wave, this is the arrival time for this one, this is the arrival time for this one, this is the arrival time of this one. So when you join them together, what you will get in terms of time and the distance, it's your travel time curve. Okay, so travel time curve for P wave I have just shown. You can similarly generate for S wave, likewise for Rayleigh wave. You need to take into account the direction also. Okay, so this travel time curve is very important because the slope of the travel time curve dt by d delta is basically your Ray parameter. And Ray parameter is a very important parameter in the case of seismology when you are deriving any equation related to the wave propagation. It's a very important parameter because Ray parameter remains constant all along the path of the ray, no matter from which material it is going through. Okay, so this Ray parameter. So similarly, this travel time curve we have the author has generated for the Rayleigh wave, and this is Rayleigh wave here. Okay, this is Rayleigh wave travel time curve. When it is going anti-clockwise, when it is going clockwise, then these are the waves. When it is going for anti-clockwise, these are the waves. Okay, so this is the travel time curve for the Rayleigh wave. Similarly, you can generate the travel time curve for the Love wave. Now, I did not do the derivation for the particle motion of the Rayleigh wave, but I can show you the final thing, the displacement of the Rayleigh wave in x direction and the z direction for the Poisson's solid. Okay, do you know what is Poisson's solid? What it is? What is Poisson's solid?
I think that point the sides.
Yeah, 0.25. It is the Poisson's ratio. Okay, so where the elastic constants lambda and mu inside of it. Okay, Lamy is constant and the shear modulus both are equal for a kind of solid that is known as the Poisson solid. For the Poisson solid, the VP by VS ratio is around 1.75 and Poisson's ratio is 0.25. Okay, so we are considering the Poisson solid here, and at the surface we are trying to look at the motion of the particle, and these are the equations that governs the motion of the particle in x direction and also in the z direction. These are the displacement. Okay, so when you look at these equations, ux is equal to 0.42 a kx. Kx is the wave number. Okay, x directional wave number, and sine omega t minus kxx 0.62 kx cos omega t minus kx. So what is wave number? Anybody?
Yes.
What is wave number?
1 by time period.
1 by time period. So little far away.
1 by lambda.
2 pi by lambda. 2 pi by lambda. So how many waves are there in a complete cycle? In one complete cycle, how many waves are there? That is your wave number, right? Okay, so yes, the gentleman has said it correctly. The 2 pi by lambda is the wave number. Okay, it is denoted by letter k, small k, and it is also equal to the angular frequency divided by the velocity, omega by v. Okay, 2 pi by lambda omega by v. This is your wave number here. Okay, omega is the angular frequency, right? Very good. Okay, and A is the peak amplitude of the Rayleigh wave. Okay, so what you see here, ux is having the term sine and uz is having the term cos. When one is maximum, another is minimum. When another is minimum, the first one is maximum, right? So basically, if you will make the path of the particle or will plot the particle motion in the xz plane, then because of these two governing equations, it will look like elliptical motion. Okay, like this. So you can see when you will individually plot the displacement ux and uz, so this dashed line here in this particular figure, the dashed line, big wiggly lines are representing the radial component, and the solid line is representing the vertical component. Okay, so vertical component and the dashed lines are both are basically out of phase, right? So you can see when one is maximum, this is maximum solid line, then it is becoming minimum. When another is becoming minimum, so the combination of both will give you the elliptical motion. So this is what it is written. Since cosine and sine are 90° out of phase, this means a particle on the surface is going through elliptical motion. Moving to greater depth, the sense of rotation changes from counterclockwise to clockwise. That means at the surface, the particle near to the surface is moving opposite to the direction of the propagation of the wave. That is why it is retrograde motion. As you go deeper, the same particle, because elliptical motion it is, at the deeper depth, that particle will be moving in the direction of the propagation of the wave. Okay, so that is why at the deeper depth it is having clockwise motion or prograde motion. But generally when we talk about the what is the particle motion of the Rayleigh wave, we generally say it as the retrograde elliptical motion. Okay, now there are some points about the particle motion of the Rayleigh wave. Note that the exponential decay of the displacement is a function of wave number kx is equal to 2 pi by lambda. Okay, since we did not go for the derivation, okay, so basically harmonic waves can be represented in the form of e to the power, okay, iota omega t plus minus kx sine, okay. So that is why it is written that, note that the exponential decay of the displacement is a function of wave number kx is equal to 2 pi by lambda. Degree of exponential decay diminishes with the increasing wavelength. So for the surface waves, it is said that it is the decay of the surface wave is a function of wavelength. So larger wavelength of the surface wave will penetrate deeper. Okay, a smaller wavelength of the surface wave will remain to the shallow surface, shallow subsurface. So this is what it comes in the concept, like if you so let's suppose this is the surface, there is one layer and maybe there is some other layer down below. Okay, and if I want to plot the dispersion curve of the surface wave here, then maybe it may look something like this. Here you have lambda and here you have the velocity of the surface wave. Okay, so a smaller wavelength will basically give you the information about the velocity of the layer that are in the shallow subsurface. But the larger wavelength, because it can penetrate deeper, can give you the information about the velocities in the deeper part of the earth, of the second subsurface, second layer. Okay, so in other words, a longer wavelength Rayleigh wave will see deeper structure in the earth. Since in general velocity increases with depth in the earth, this makes Rayleigh wave dispersive. Because you can see when I am plotting the dispersion curve with respect to wavelength, it may look something like this. Okay, so you have the velocity. Okay, here you have on the y-axis you have the lambda wavelength. So velocity is varying with respect to the wavelength. Okay, that is known as dispersion phenomena. Or if you want to look at it more physically, if I just draw the surface wave, just notice what I am doing. Okay, I am just plotting the surface wave here. So see, this is the surface wave. So what I did, here you have time. This is the time axis. So you can see while plotting the pulses, I tried to reduce the distance between the peaks in time. Okay, so that means individual components are basically traveling with different speeds. That is why that kind of phenomena is occurring. The peak to peak distance is reducing. Okay, that is so. that is why the dispersion phenomena is observed in the surface wave. Okay, so in general, the velocity increases with depth in the earth. This makes Rayleigh waves dispersive. This dispersion can be measured to infer the depth variation of the velocity in the earth. Okay, so you might have read those who are little bit familiar with seismology. So like, or maybe seismic site characterization they might be working on, or maybe they have conducted some kind of MASW surveys or SASW surveys. So all these curves, dispersion curves, are basically used to model the velocity structure of the area of interest with respect to depth. So you will try to basically invert these dispersion curves in order to find out the shear wave velocity structure underneath the area of investigation. Okay, so this is why it is very important. So here you see this record section.
Because I think everyone is.
Yeah, I will provide you the note. Okay. Not the note, the entire slides I will give you. Okay. I think that is what we have been doing so far.
Yeah, I mean, it's amazing.
Okay, so
Look at this particular figure. You will see, what do you see? Do you make any intuition about it? Like, so this you have seen previously, this curve. Here, this one. Sorry. So this one. This curve you have seen. So this is the travel time curve of Rayleigh and the Love wave, right? And when you observe the Rayleigh wave realistically, then also you observe similar type of travel time curve. Okay, with time, and on the x-axis you have the distance. Distance is given in degrees. Why distance in degrees is there?
distance should be in kilometers. I can set in the now I should think. It
Coordinate space at the mountain to see
so you might have heard 1 degree is equal to 1.2 kilometers,
you.
right? 111.2 kilometers. So basically you are considering the convention of the earth. Okay, so the between the source or epicenter to the
Measuring station, the distance, instead of measuring it in terms of the kilometer, you are considering in terms of the degrees. Okay, if you want to convert it into the kilometer, then just multiply it by 111.2 kilometer, right? So this is the record section formed from vertical component of the seismograms at the stations of the international deployment of the seismometer network. Okay, there is so that is some network where the records has been recorded for the vertical component only. So on the vertical component, the Rayleigh waves are most visible, right? So you can see, look, this is R1 here, this one is R1, this is R2, this is R3, this is R4, likewise. Okay, this is the same section, but because the same section, such a large section, you may not be able to see, so that is why it has been kept in side by side. So you will see there is dispersion phenomena is happening. They are spread in time. So this dispersion, these are dispersed in time, right, like this. So this is basically you observe in the realistic seismogram. Okay, that is basically happening due to the heterogeneity present in the earth, and because of the dispersion phenomena happening onto the in the surface wave. Okay, so there are these are some points. Surface waves can circle the globe many times after a large earthquakes, and the figure that we just saw shows multiple surface waves which are denoted as Rayleigh wave, Rn, Love wave, Gn. An important feature of surface wave is dispersion, the fact that the waves of different periods travel at different frequencies, different velocities. or you can say different frequencies are traveling at different velocities, or you can say the different wavelengths are traveling at different velocities, all are same thing. Okay, an important feature of surface, as a result, the surface waves arrival are not sharp. So here you don't see sharp arrival. So you can see they are spreaded in time, right? Here also they are spreaded in time. They are not sharp. Okay, so they are spreaded because of the phenomena of dispersion. As a result, the surface wave arrival are not sharp line but are spread out of time. So what is dispersion? Dispersion means that the wave velocities are dependent on frequency. As an example, Snell's law tells us that, what is Snell's law?
Just recall, what is Snell's law?
Entire when cycling was going to an English. Was slightly like well
Yeah, you're right, actually. Yes.
forecast in
Very good, very good. Yes, please.
side by on side I by side are parted to given by continuous with request
Yes, very good.
the worst inside.
Yeah, Snell's law basically relates that the ray parameter L along the ray are constant. Psi A by B is what?
Savage.
Ray parameter.
Something.
Okay, so ray parameter along the path is constant, even though the ray is traveling from one medium to the another medium. Okay, if we were considering the curvature of the earth, then R1 sin I1 by V1 is equal to R2 sin I2 by V2. That is Snell's law, right? So, as an example, Snell's law tells us that the index
Of refraction of light in a medium is dependent upon the speed of light in that medium. Yeah, that is what we just said, right? So, however, the speed of light in a medium is often frequency dependent. Hence, in a raindrop, different colors will be refracted by different amount, giving us a rainbow. So, same phenomena happens in the case of surface waves as well. Okay, different frequency component are traveling with different velocity, right? So, more technically, dispersion implies V, velocity, is actually a function of wavelength, V in bracket lambda, velocity depending upon the wavelength. Okay, that is the dispersion phenomena. And the velocity, so basically velocity can be written as the angular frequency divided by wave number, right? So velocity is equal to omega by k. Okay, that is the relationship that represent the velocity as a angular frequency divided by wave number. So for a particular angular frequency, velocity will be different. Okay, so another way often used to represent dispersion is to give the relationship between angular frequency, angular velocity omega and wave number k. We know already that the velocity is a function of these two parameters. Okay, in a dispersive medium, this omega will be a function of wave number. For instance, shorter period tsunami wave follow omega is equal to under root gk. So what is tsunami? You know tsunami, right? When there is a earthquake inside the ocean, because of the fault displacement, the column of water will be displaced. Okay, the potential energy will keep on converting into the kinetic energy. As it reaches to the shore, again it will be converting into the potential energy. Okay, so it will give rise to the higher amplitude of the tidal waves. So that is what it is known as tsunami. In tsunami also dispersion phenomena happens. Okay, so that we will come to that. So in dispersive medium, angular frequency can be written as a function of wave number. Okay, short period tsunami wave, the angular frequency is under root g and k. What is g? G is the acceleration due to the gravity, k is the wave number, and we can solve for what this means in terms of the velocity. V is equal to omega by k, and that is equal to under root gk by k. So So dispersive relation are given often in the format of frequency as a dependent upon the angular frequency and the wave number is equal to 0. So for the tsunami example, dispersion will be represented by omega minus under root gk is equal to 0. So just forget about this slide for now, because this slide will come back again. There you will be getting to understood it in a more better way. Okay, to explore the dispersion further, you are required to consider the net effect of the two harmonic waves with slightly different frequencies and the wave number. Let's suppose there is one harmonic wave having omega 1 as omega naught plus delta omega, another harmonic wave omega 2 is equal to omega naught minus delta omega, and k1 is equal to k naught plus delta omega and k2 is equal to k naught minus delta omega. Okay, so if you want to write the equation of displacement consisting of these two frequencies and these two wave numbers, the wave equation can be, if you are considering maybe let's suppose unit amplitude waves, then the displacement will be the summation of these two waves, right? So first wave is having cos k1x minus omega 1t, and another wave is having cos k2x minus omega 2t. So do you remember the differential wave equation? Del square u by del x square is equal to 1 by v square into del square u by del t square, where u is the displacement, v is the velocity of the wave. When you go for the solution of those that differential wave equation, then one of the solution is the harmonic waves. Okay, so a e to the power iota omega t. Okay, that is the solution of that particular differential wave equation. So similarly we are using a unit amplitude wave here. Okay, so the total displacement will be the summation of those two waves. Okay, if suppose two waves are traveling and they basically superimposing with each other, the net displacement will be the summation. So summation is cos k1x minus omega t plus cos k2x minus omega 2t. Okay, if I will ask you cos k1x minus cos kx minus omega t, if I will say there is a wave, its equation is, displacement equation is u is equal to cos omega t minus kx. So what is the direction of the wave? Is it x direction, positive x or negative x?
Positive x direction or negative x direction?
But
Yeah, minus. There is minus sign.
it is short.
Constant.
Something and that's negative.
It's a positive x direction because phase remains constant. Omega t minus kx will remain constant and time is keep on increasing. In order to keep the phase constant, you need to increase x. That means x is moving in positive x direction. Okay, if suppose there is positive sign omega t plus kx, then you need to keep the phase constant, then t is increasing, then in order to keep the phase constant, x should reduce. So that will be negative x direction. Right? So okay, we will continue with this in the next class. Thank you so much.